Hi, my name is João Cardoso, and I am the tutor of this session 5 of Model 4 on safe roads. In this session, we will address the methodologies to assess the effects of road safety interventions. The issues to be discussed are applicable to any type of road safety intervention, not only those on road infrastructure, but also those that are applied on other elements of the traffic system, such as those applied on vehicles or to enforcement. As you know, this model on safe roads is concerned with the influence of road characteristics on accident frequencies and severity and how they may contribute to higher safety levels. In this fifth session, we will present key scientific concepts for road safety analysis. The main principles being described relate to two broad questions: how to evaluate the safety level of an existing road element, for example, the suburban road shown in the picture, and how to assess the effect of safety interventions on the safety level, for example, the effect of the change to a more urban setting. So in this session we will deal with three main topics: probabilistic approach to accident frequencies, factors influencing registered crash frequencies, and assessing the effects of road safety interventions. Considerable specialized expertise is usually required to fully apply the methodologies mentioned in this session. However, this session is not intended to teach you how to design and implement a procedure for assessing the results of road safety interventions. The major motivation is just to raise awareness to a set of important issues that need to be addressed when evaluating the effects of road safety interventions and to inform on methodologies and procedures that are available currently for dealing with these problems. This information is important for setting out contract terms of reference and for evaluating the quality of the study results. It is assumed that the tools, and especially the statistical tools themselves, will be developed and applied by experts and not by normal people. Ideally, it is generally accepted that the road safety level of a transport system element can be measured by the long-term average expected number of accidents of that element. The question then is how to measure in practice this long-term average expected number of accidents. In the early 1980s, Erza Howard, in a breakthrough paper, showed that the registered annual number of accidents is usually not a good estimator to this value. In this slide, we use a similar procedure to Erza Howard's, but with accident data from Portuguese roads collected in the 10-year period from 1994 to 2003. These roads were divided in 1 kilometer sections. In the two leftmost columns of the table, we have the number of sections that had 0, 1, 2, 3, 4, 5 and accidents in 1994. In the following 9 columns, we have the average number of accidents in each group of sections in each year. For example, 78 sections with 2 accidents in 1994 had an average of 0.64 accidents in 1995, 0.83 accidents in 1996, and so on. We can also notice that the lone section that had 5 accidents in 1994 had 0 accidents in 1995, 4 accidents in 1996, and 2 accidents in 1997, and so on. We can see also that the 5 sections that in 1994 had 4 accidents had 1.4 accidents in 1995, 1996 and 1997. In this period, the Portuguese road network operation policies focused on constructing new roads rather than correcting existing ones. This means that the majority of the sections described in this uh, slide were not changed or improved in the period analyzed. However, as we have seen, the number of accidents in 1994 is a poor predictor for the number of accidents in the following years. This means that if we select a section with a high number of accidents, for instance 4 or 5, the number of accidents in the following years in that section will be lower, even though there are no changes in the infrastructure and traffic system. This is a common statistical phenomenon that can be found in many distributions and was first described by Francis Galton in late 1870s when studying the inheritance of human heights. He found that the descendants of tall men tend to be shorter than their parents on average, just as we noticed for sites with many accidents in one year. In succeeding years, the number of accidents will most likely fall, even if no interventions are made in those roads. This phenomenon is called regression to the mean. In this slide, we have a similar exercise as in the previous one. However, here the numbers of accidents are aggregated by periods of 3 years. Overall, the same pattern of regression to the mean can be observed. On average, the number of accidents in the following periods will be lower than in the initial or reference period. You can see also that the differences are not so big for this case as they were in the previous slide. So at this stage, you can see that the question on how to estimate the long-term average expected number of accidents is not a simple one. So clearly, we cannot trust the observed number of accidents in a year to do that job properly. We also have reasons to be suspicious concerning the use of simple aggregated averages. Currently, the state-of-the-art for estimating the expected crash frequencies is the empirical Bayes method, in which the observed data on accident frequencies in the analyzed traffic element is combined with knowledge on the safety level of traffic elements similar to the one we are analyzing. In this approach, it is assumed that the observed number of accidents is a combination of a random component and a systematic component, this one corresponding to the average expected number of accidents. Incidentally, the systematic component is seen as the result of a combination of general factors which are common to the type of traffic element, for instance a four-arm intersection, and local factors specific to the analyzed site. Local factors can be, for instance, a high percentage of left-turning morning traffic in the eastbound traffic arm of the intersection. According to several authors, 6 main broad categories of factors may explain the observed variations in the number of registered accidents. There are autonomous factors, such as weather, the price of oil, or population, which at a given moment are not influenced by a government. Socio-geographic and economic factors are those that are subject to government policies which themselves rarely have road safety or even transportation as their main purpose. Employment, taxation, public education, and so on. Transportation sector policies such as infrastructure construction, transit level of service and fares, modal choice policies, active mode promotion, fuel taxes, and so on, are not usually directed for road safety, but have an indirect effect on the safety level of the transportation system, namely through changes in exposure. Broadly, road safety interventions are actions designed to target consciously chosen safety performance improvement objectives within the road transport system. Changes in reporting procedures and protocols may also change underreporting rates and therefore have an influence on the observed accident and victim counts. Finally, as previously mentioned, accident counts are influenced by randomness in a similar way as the roll of a die. However, in the case of crashes, this variation is especially evident in those road elements that have small long-term average expected crash counts. When assessing the influence of infrastructure factors on the registered accident frequency, usually the amount of traffic is a key variable. Traffic can be expressed by the number of vehicles per unit of time, traffic volumes, or even by travel distances. Normally, for simplicity, the relation between the number of crashes and traffic flows is assumed to be a monotonous one. That means the number of crashes per unit of time increases with the number of vehicles, as in the graph on the left. The reasonableness of this hypothesis depends on the level of aggregation of the analysis. Usually it is acceptable, for instance, at the network level. However, there are cases in which non-monotonous relations provide better representations of what happens on the road, both theoretically and in reality. For instance, when analyzing run-off-road accidents on motorway link sections, it is reasonable to expect that for low traffic volumes, the number of crashes increases with increasing traffic. However, for very high traffic volumes, at level of service E and approaching traffic capacity and beyond, more traffic means lower speeds and lower opportunities for crashes, and so a reduction in run-off road accidents is expected. The graph on the right shows this type of relation as fitted to Portuguese motorway crash frequencies on link sections. When discussing causal mechanisms explaining the effect of the implementation of infrastructure correction, Runelvik hypothesized that safety interventions in the road infrastructure change the basic risk factors, which in turn modify the structural safety margin available for road users, resulting in a new level of safety, as expressed by the underlying long-term average expected number of accidents and victims. This means that from a physical point of view, it should be possible to evaluate the change in basic risk factors due to an intervention and also the resulting change in the level of safety. However, human factor aspects strongly influence the traffic operation and also the effect of interventions. In the pictures, we have examples of changing the stability of vehicles with higher center of gravity and also the non-use of available protective devices which change the risk of injury. Also, institutional factors play a role. In the example shown, the road administration decided to use the traditional solution for obstacles. That means shielding the traffic with a safety barrier. However, a more efficient solution would be to cover the drain box and obtaining a proper continuous and regular clear zone. This slide shows examples of cultural and organizational factors that may also affect the potential change in structural safety margin. Here we have the impairment of pedestrian safety by diverting the original use of sidewalk space for other uses, for the benefit of individual or institutional actors. So Runelvik then separates the engineering effects from the behavioral effects and states that these may influence both the change in the basic risk factors and the safety margin by means of behavioral adaptations. As a consequence, the resulting level of safety may be different from the one originally anticipated, and thus road safety intervention results should always be assessed. Road safety intervention results and effectiveness can only seldom be evaluated through classic experimentation, that means randomized control experiment, due to both practical and ethical reasons. So, traditionally, this evaluation is made through observational studies, either using accident modeling or before-after studies. In the first case, crash frequency and severity cross-sectional models, as the one presented in slide 10, may be used, especially at a disaggregate level. At the high aggregate level, time series modeling is also popular. Before-after studies may be used at an individual level, studying a set of road safety interventions individually. Given the results from a series of before-after studies on a given type of road safety intervention, a meta-analysis may be also applied to improve the calculation robustness of its anticipated effects. Basically, a before-after study consists of four main tasks. We have to estimate the safety level of the road elements in a time period previous to the road safety intervention application. That's the before period. We have to estimate the safety level of the road elements in a time period following the road safety intervention application, in the after period. And we also have to estimate the safety level of the road elements if the road safety intervention had not been applied, and also in the after period. And then we have to use an algorithm to compare both developments. The most basic process is represented in this slide. On the left part, we have the observed safety development previously to the road safety intervention. Then there is in the middle the implementation of the road safety intervention. And after this application, we have on the right side the observed safety developments. That's the bottom points and line. Also on the right, we have the representation of the anticipated safety development if no road safety intervention had been implemented. As we have seen in previous slides, several factors may influence the registered developments in the after period, besides the road safety intervention we intend to evaluate. Typically, road safety interventions are applied on sites where safety levels are lower meaning the crash frequencies are higher, for example, at black spots. As we saw previously, on these sites, due to the regression to the mean effect, it is likely that the number of crashes will diminish in the after period when compared to the before period. Developments in traffic volumes, long-term trends in accident frequency and severity, changes in accident registration procedures by the police and other events may influence road safety level in the after period. All these confounding factors must be considered and addressed in the comparisons to obtain a robust and valid evaluation of a road safety intervention. Known causal factors such as regression to the mean, traffic developments, and overall long-term crash risk trends may be considered explicitly by statistical models if the underlying variables are measured and understood. Consideration of unknown causal factors is only possible by time series comparisons or by way of using a control group of unchanged sites. In this case, it is assumed that the effect of the causal factors has the same magnitude in the analyzed site and in the sites of the control group. This means that the selection of the sites in the control group is critical for the comparison. Similar sites and similar road safety developments in the before period are required. Then the complete picture for a proper before-after study must then include also the development of road safety on the control group sites before and after the intervention at the corrected sites. The control group data in the picture is represented in red and the corrected site in blue. In this case, the estimation of the anticipated road safety in the corrected sites in the after period takes in consideration both the regression to the mean effect and the developments in the control group sites. There are several ways for comparing the developments in road safety level at the control sites and at the corrected site. One of them is to use the Turner K-test, as shown. Estimating the true underlying crash rate of a site and correcting for the regression to the mean effect can be made in several ways. For example, Hauer developed the empirical Bayes method and extended it to applications in before-after studies. However, in some cases, it is possible to use one ingenious way to address regression to the mean effect that was devised by Abes, Wright, and Jarrett, using the accident frequencies of a set of sites similar to the one that is being analyzed, and which constitutes a control group by itself. The equation in this slide shows how to calculate the percentage change in the crash frequency that may be accounted for by the regression to the mean effect. In the next two slides, we show examples of the application of the regression to the mean correction and also how to use the Tanner K-test for evaluating change in accident frequency relative to control group. In this example, we are dealing with the treatment of a forearm intersection where in the before period of 3 years, 15 crashes were registered yearly, and in the after period 10 crashes were registered yearly. As a control group, we have 83 forearm intersections, which had registered on average 11.3 crashes per year in the 3 years analyzed, with a variance of 2.75. Following the use of the equations shown in slide 23, we conclude that the 15 yearly crashes in the before period correspond to 12.1 crashes if we deduce the effect of the regression to the mean effect. That means that if nothing had been done, in the after period, we would expect 12.1 crashes yearly in the treated site. Therefore, to calculate the effect of the intervention, we have to compare the observed 10 yearly crashes per year during the after period with the 12.1 yearly crashes that would be expected without intervention. And the result is shown in the last equation of the slide. In this slide, we show the use of the Tanner K-test to evaluate the change in crash frequency relative to the control group. So this concludes the session 5 of Model 4 on safer roads. We have seen that distinct and numerous factors affect the number of registered accidents and injury victims. It is important to properly assess the real effects of road infrastructure safety interventions. Usually, regression to the mean has to be addressed. Exposure impact on accident frequencies may be considered by road safety functions properly fitted, and unknown causal factors may be considered by comparison with the convenient control group or time series analysis.